Okay. Hello, everyone. This is Nagarjuna. Uh, Topic for today is our the most recurring topic, that is recurrence. So, like I think Bhavish or somebody mentioned, like we have talked about it before, and like it comes up in a lot of topics that we discuss. Like whatever we pick, stacks, linked lists, or binary search, or anything. I think most of the topics that we discuss, we get the recursion. So the attempt that I'm trying to do today is like there are several ways when you look for online resources. There are several uh, resources that are available to solve different recursion problems. I've seen like um, not not like promoting them, but I've seen in Byte by Byte they have some patterns, and like Abdul Bari they have some ways and all. So I've recently seen one of that such resources on YouTube, Aditya. I've actually following the dynamic programming, and this was started on recursion. So I found two interesting approaches there. So the problems that I picked today are using those approaches. So let me share my screen, and uh, you should be able to see my screen now. Okay. Let me know if anyone is not seeing my screen. So the two approach, the couple of approaches we discussed. I picked two of them for today's session. One method is like a base condition hypothesis induction method. The other one is recursion tree method. So these are the two methods using which we could solve two different kinds of recursion problems. So starting with the first one, this method uh, is the way where you actually reduce the input using this method, this base condition hypothesis induction method. So, so to explain about this method, hypothesis is like you say that you have a function, whatever the problem that is given to you, you say that you have a function that solves the problem and that somehow gives you the solution. And recursion, a lot of times when you look at the code, it's like a very limited code, and you see and you find that it solves the problem. There's some, like something magic going on the back. So you say that you start with that, saying that you have a function that really solves the problem, and then you have a base condition where I think in all the approaches of the recursion, you have this. You have a base condition where you know where to exit the exit the loop, and the induction is where the logic where you write to um, logic that you like to combine the results that you get. So in hypothesis, the way let me take a simple example. I have one simple example. So let's take a simple example where you want to, so you want to print the numbers from to n, right? That's a simple one. You could actually simply write using a loops, any loops that you have for loop and f loop, but we are just trying to force it to use recursion to do it by using this solution, which is hypothesis, base condition, and induction. So always hypothesis, in the hypothesis, what you say is um, for a smaller input, you take for a smaller input and you say that this function actually gives you the solution. So here you say like I have an n numbers. So this is a method. I mean, like this is the method that works in. So uh, follow through this. I think if you take more examples, then it will make more sense. If it does not really make sense on the first attempt, but so what it says is like you take in smaller input and then say that this works. This print function, whatever you have, you assume that that works and that actually solves the problem for a smaller input. For example, here I have taken like uh, number 8, print numbers from 1 to 8. So I say like, okay, this function will solve the problem for me from 1 to 7. It solves it somehow. That's the hypothesis, right? And then you have a condition, a base condition. Base conditions are usually like the the smallest valid input or the largest invalid input. I think it makes it comes in as for different problems, but it's usually like the smallest valid input or the largest invalid input is the base condition. And induction is like, okay, now you have taken out, you say like from n to n minus 1 to you were asked to solve problem for n, but you said like n minus 1 I have a solution and what to do with n. So here you are asked to print it, just print the numbers. So it says you print it, and that does the trick. So let me run this and see like this hypothesis induction base, and now when I run it, oh, sorry, it prints the numbers, right? So that's the idea. So with that idea, we can go to we can pick one of the problems, and that's also it's not a new problem. It's just the regular problem that we have seen, but it's just using this principle of base condition hypothesis induction, this method of solving the recursion problem, where you get in the cases where you actually reduce the input and solve the problem. So the problem that we will pick, the first problem that we'll pick today is the reverse stack problem. Before I proceed, and that did make sense? Any questions? Okay, so I'm assuming that is good.
It made sense, yeah.
Oh, thanks, Ankush. Yep. So this is another straightforward problem, right? Reverse stack. So the condition here is like if you were to do reverse stack, probably like if you were not using recursion, if you are not asked to use recursion, and if you are allowed to use space, then you just pop and put in another stack, and then that's done, right? Then the stack that you create newly is a reverse stack. But here the conditions that are given is to reverse the stack using recursion. You're not allowed to use loop constructs like while, for, etc. I mean, basically we are forcing ourselves to use recursion to understand like how this works, and use these methods to reverse the stack. Okay. So I mean, like I want to explain how we could use the principle, the base condition, to make it short. I'll say like BHI method, to use the BHI method to solve this problem. But if anybody has like general ideas of like how you would have solved it using recursion, please feel free to share. Then we can also look into like how BHI method can be used to solve this problem. Any thoughts on like how you do in general using recursion? Yeah, I can go ahead and start with the BHI method as well. I don't know. Have you guys tried this problem? Anyone of you tried this problem? Because I don't think anybody would want to try this in a recursive way, right? Reverse the stack.
Okay, so for me, I would think when it's empty, the best case when it's empty would return, right? Otherwise, we pop it out and we print the value.
Yeah.
But because when we know that by the time it's empty, that have to be the last element, and when we pop it out and we print the value, and then we push it back, right? Because we don't want to make the to mutate the stack.
Right. But when you push it back, like you still have some elements in it, right?
Yes, you can, because I'm thinking if this is the last element, right? It's empty.
Right,
so
right.
I pop it out, right? I print it. Then when I push it back, when they go back to the previous recurse, it already have that value. So you know it printed out, it popped it back. So I think initially it go in, it take the value out, and it recurse, right until it's empty.
Yeah.
And then it print the value and it push it back to the stack.
Right. You have to wait until if it is empty, you push it back, and then yeah, you're right, Leon. It's actually in that. Let's see. I think the thought process is same, but let's see if we can put it in this mode of like the BHI method and see like how it helps. So like we discussed, the hypothesis is like you make an assumption that the smaller input gives you the solution, right? In the number case where we said like I want to print the numbers from 1 to 8, I said like I have a solution for 1 to 7, right? I have a solution for 1 to 7, and I say like, oh, that's my recursion function that somehow gives the solution. That's the hypothesis. And then the base condition, you have like lowest possible input or the lowest possible input. In this case, it's like when the stack is empty, then you're done. And then the induction is the place where you have the core of the logic, and like you have taken out the number, one number, and you say like for the rest of the numbers, I somehow get the solution. That's the hypothesis. And then what do you do with that number, right? That what you picked. So in this case, the I don't know if I can draw it here. Can you guys can I do it? Draw. Okay, I think it's white, so it's not showing. Does anybody know? I am not able to select the color. It's actually by default white. How do I change? Bhavesh, do you know?
Like if you're looking for the PDF, like
you can go to the format.
the PDF, yeah.
There you have a lot of colors.
Format this. Oh, okay.
You can download the PDF and then you should be able to.
I'm able to draw it, but it was selecting white by default. So
Format will have different colors.
yeah. Now I got it. Okay. So this one. Yeah.
Yeah,
So
it's visible.
yeah, it's visible. Okay. So now we are saying like we have 1, 2, 3, 4, right? This is the stack. And now we want to reverse it. Now we say like the hypothesis is like, okay, for in case of numbers, we said like n minus 1. In this case, we could say like, okay, for this, I have a solution. And now I have in the induction, what we did earlier was like just print it. Now we have this one. What do we do with that? That's the induction. Like what do we do with it? So what we can do with this is like we have to insert back into the stack. So that's what we have to do. Like, and when do we insert it? When it is empty, you insert it. If not, you take them out and then insert it. So that's the induction logic. And you say like for n minus 1, we have a solution, and for 1 you're trying to solve. When you're trying to solve for 1, what you do is like you want to insert it back into the stack, because we want to reverse in place in the stack, right? So we want to insert it back. So if you take like just insert as one function, we can look into like how we want to insert it. That becomes another recursive problem where you say like I have an element on the top of the stack, you want to insert it back. What do you do with that? That becomes another problem. But just to get the hypothesis of it, you say like for n minus 1, for the not but the top element, you have a solution and you just have 1 on the top, you solve for it. So I can, let me share the code. It will, it's a simple code. It should make sense.
Essentially, Naga, we try to insert our current element at the bottom of the already reversed stack, right?
Yeah, at bottom of the reverse stack. But the operation is insert. That becomes another recursion, but the inserting is the induction part. Now we can take that particular insertion itself as another problem, where you have one element on the top, you want to insert it in the bottom of the stack, right?
Right. Got it.
And that also becomes another recursion problem here, where you say like you have top, you want to insert it back. Whenever you want to do that, then again you follow the same principle here in a hypothesis, where you say like, okay, if I know that I can insert it if how do I insert it if it is empty? How do I insert it when there are values? When it is empty, that becomes a base condition. You insert it directly. When you have elements in it, what you do is like basically you
Save them somewhere.
yeah, save it. You
In the recursion only we can save like
yeah.
yeah.
In the recursion you save it. I mean, when you save it in the recursion. So since I'm trying to stress on this hypothesis, I'll again talk in terms of that. So reverse the stack, right? So same principle here, what we have done before. First, we say hypothesis, which is this one here. Here, in case of this one, we say like make the input smaller. The way we make the input smaller here, earlier it was like n minus 1. Here, what we say is like we pop the element from the top, and now the stack has become smaller. Now we say like, okay, this reverse stack hypothesis would give you the solution. And now what do you do with the element that you have, right? So that's the induction. Earlier it was like print, so we printed it. So this is the solution, right? As simple as it, like it says, like it's still working in the way of like hypothesis and induction, this one. And then insert thing comes in, right? So it again follows the same thing here. What you want to do is insert. So let me collapse the base condition. Base condition is like when the size is empty, you don't have anything to do, so you push it in. So the hypothesis is like you are able to insert into it when in an n-1 solution. So that's what you did a pop, you're able to insert into it. And then, yeah, this is what you picked it out. And then you push the element. Did it make sense, guys?
There is one problem. On line 33, we don't have this API. We can only check whether it's empty or not.
Which one?
Line 33.
Oh, you're saying like in the hand.
Question?
Yeah.
Yeah, so we have only is empty API, not the size API. So we will never know that now the size is 1 or not.
I think what we are doing here is only checking if the
so I'm fine if in the insert method, there where you check size is equal to 0. So I'm fine with this because you can easily replace with is empty.
Is empty, yeah.
But yeah, but line 33.
I don't know if empty is there in the
yeah, there is the C++ stack. There is empty.
There is.
Yeah, there is.
So that's the reason I believe we used size, because this is talking more in terms of like all the different languages basically.
Why can't you just If it's empty, just return, else you pop the element. I mean, you can modify the original reverse stack method itself. No need to call the second recursion.
So when you want to,
So
right?
you popped. So I'm saying when you pop the element, it's now your hypothesis is that if the remaining stack, we should be able to reverse it and then
Right.
push this temp element. So just replace this insert line with s.push temp. That's it. It should reverse the stack, I guess.
No, but
And
that has to be done recursively. You have to
pardon me?
do the same process again. Like when you try to insert a particular element, you again have to go down and do it recursively. So you cannot do like just push.
Yeah, but this is how our hypothesis is working. We are, so after this reverse stack for lesser, so the smaller stack, we assume that it's already reversed. So only we need to insert the element on top of it.
Yeah, it's insert the element, right?
So insert means push. So okay,
Where do you
So it,
insert it?
I mean, if you comment this insert line on 40 and just do s.push temp.
no, it's insert at the bottom.
Yeah.
No, you don't need to, because your hypothesis at line 39 is your stack is already reversed.
Right. Let's
Yes.
see. Let's take a diagram if you want.
Okay, got
Or
it.
you can run the code as well. That also shows
Yeah,
the way
yeah. Okay, you're right. Yeah,
it would push it on the top, right? What we want to do is insert it at the bottom.
yeah. Right.
Yeah.
But still, well, we can use size, but we can do something. But in question is said that we don't have size API.
Even if we have, I couldn't think of anything because you have to do it at the bottom. So, and in stack, like if you want to do it at the bottom, that's the way, right? So that's the reason I thought it is like this.
Mm.
Pushing would just do on the top. Here, the push is like you make sure it is you are at the place to push it to insert.
Yeah, I got it. Yeah, so you are just so second recursion, you take out all the element, push it at the bottom, and then reinsert again.
Yeah.
Hey, can you please explain again what is the difference between induction and hypothesis? The recursive call, I mean, at line number 39 is part of hypothesis, right?
Yeah, that's hypothesis. In hypothesis, what we say is for a smaller input, that solves the problem, and that's what you assume it. And whatever the element that you have, right, for the element that you picked, which was not part of the smaller input, you try to solve for that. So here, what we are saying is, in this case, s minus 1, which is like you remove the top element and you said like it's solved for this problem, right? So it's like you somehow say like, okay, now the stack is all reversed and ready. Now what do you do with this element, the element that you have on the top that you picked out, right? So now you have to insert it. So like we were discussing, right, if you push it, it goes on the top, but what you have to do is you have to put it at the bottom.
Yeah, makes sense.
Yeah, induction is the core logic of the code, but that helps in this hypothesis helps in like assuming that you have already solved for the reduced input. That they call as magic of recursion. That's the reason where you see like a lot of recursion code, though the problem sounds like too big and complex, the recursion takes care of a lot of these things. This is one method of solving. I've seen like a couple of problems where this worked, where your primary goal is to keep reducing the inputs and solving it. You basically don't have anything like decisions, choices, and all that kind of stuff. There are such kind of problems also where we solve using recursions. But this is that, and I found this interesting because there is two such problems in the same thing. It is like where you insert it and where you.
Which one is the second problem?
And Yeah, let's talk about the second problem. I'm just saying, like, you mean to say what were there in the same thing? Insert is again the same, following the same approach, right?
Hey, yeah, sorry. For this question, on line 33, if you replace that if by s dot empty and just return if that's the case, I think that should work, right?
Okay, so as what we want to do is if size is equal to
I
1,
think
return,
that
like
should,
it's nothing to do. I don't know if there is empty.
I think that should work because your first operation is a no op in that case. You reverse the rest of the stack and then insert. So yeah, you can just compile and check if that works for you. Yeah.
Yeah, I think it did work. It did work. Oh yeah, there is empty actually. We could have used that. Yeah. No, what is this actually? That's wrong.
It should be s dot empty. Yeah.
Yeah. Crazy. Did work anyway.
It worked, right?
It worked. It worked actually. I did use it to print it.
Yeah, I don't think you actually need that size check.
Yeah. Cool. Good to know. Thanks. I think we have one more problem using the same BHI method, the hypothesis induction method. Does anybody have any other questions on this? This is just about this approach. I think there might be other ways to solve this as well, but getting used to that approach to solve when you are like just reducing the inputs and using the hypothesis. Should we go ahead with the next problem? I think there's
One thing,
that.
the complexity would be n square, right?
Yeah, I haven't really looked into the complexity because just trying to demonstrate. So let's see. Actually, that's a. So to reverse the stack, it is O of n, but you always insert it, so you remove all of them.
Yeah. So the recurrence, according to me, would be if
Mhm.
t is the function, so t of n equals to t of n minus 1 plus n, because insert would take O of n time.
Right.
So that boils down to n square, I think.
Oh, isn't it like O of n plus O of n? Insert is O of n, and
I think insert is O of n square only because you try to insert 4 at the bottom. So you go all the way down, and similarly you do for 3. And
yeah, for every element I do this insert on this one, O of n square. Yeah. Yeah.
yep, okay.
Okay. So maybe we can move on to the Tower of Hanai. I believe this is quite famous problem. We could try to solve this problem also using the same approach, base BHI method. A little variation, but again following the same thing. Like you solve it, you have a hypothesis, and then use that to solve the problem. So. Does anybody want me to explain like what this problem is like? Actually, we can take. I can give you some time to read through it, and we can go over the conditions. And I also have this a simple animation that I found online, so you could also do that. But this is I think this is a very common problem that we see. I'll just give one moment for anybody new who haven't seen this problem before.
So are we given the source rod and the destination rod?
Yeah.
Okay.
Here it's only, I think, again, it's just for demonstration. So we're given, we're asked to give the, print out the steps and maybe the count. Count, I think there's like mathematical formula also to get the count. You don't really have to do the algorithm and all. Okay, so let's look at the animation. That way I can explain. Let's start. So basically what we have is we have a source. We have 3 rods here and we have 3 disks here, and that could go to any number of disks. This 3 is constant, but the number of disks is variable, so you can have any number of disks. So, and the problem you have to solve is like move this disk from here, from this source to the destination. You can use this helper rod to do that. And the reason you would need the helper rod is like there are a couple of conditions where you can only move one disk at a time, and you cannot put a bigger disk over a smaller disk. I think those are the only 2 conditions that we have, and move from this rod to this rod. So that's the problem, and you have to find out what are the steps needed to do that, and how many steps is also good. But I think there is a mathematical solution, like just a formula to do it. We would also do it in the programmatical way, but so that's the problem. So you could, if you see, the way it is solved is like remove here, and every step is counted as this one. So you needed like 7 steps to do this, and the way you do it is like you move from source to destination, source to helper. Oh, sorry, did I miss? Yeah, and destination to helper, and source to destination, helper to source here, and then so this is done. So we need 7 steps. So we are asked to identify what those steps are and how many steps you need to solve this problem. So this is constant, and the 3 rods are constant, but the number of disks could vary. So if you restart, and you could, so if you see this, just for the time, just for the interest of time, I'll just put 4. So you can, if you see the way it moves is like, you could see a pattern while this is happening. So that's the reason I was trying to put it here, which fits in with our BHI method. So it needed 15 steps to solve this problem. And you could see like this kind of some kind of a recursion happening on this one, whether that is 3 or 4 steps. Okay. So, and again, we know that this could, the hypothesis solution would work for this one. So does anybody have any thoughts or any ideas on this one? I know this is a bit very common problem. So if anybody wants to talk about that, yeah, please feel free. Again, I'll put again in view of BHI method to explain the problem solution. But any thoughts or anything based on what we have discussed so far? If you want, please go ahead. Okay, should I go ahead and talk how we could use this method on this one? Any initial thoughts, guys? Anything?
It seems that there are
Mhm.
three big scenarios, right? When you solve for one disk, when you solve for two disks, and when you solve for three disks.
Mhm.
I think if we solve those three scenarios, we can solve for any. Does that make sense?
When you solve for one disk, two disks, and three disks.
Yeah.
Okay. So you mean, so if we take this like this, so when there is, okay, you're right. Okay, let's, I don't think they're allowing below 3. I don't know why. So if you only have one disk, it's just like putting into source to destination.
Right.
And when you have two disks, you have like take a helper, put this here, take a helper and do it. That's kind of, yeah, I think that's the base of it, like how you solve it. And the reason that they have like this 3 disks is like once you solve for this, it kind of helps in all the other scenarios, like 1, 2, 3 disks. That's true.
And then you just switch the helper.
Yeah.
Depending on the, yeah.
Switch the helper depending on what you want to do, right? So in 3K, you have, yeah, that's right. So that's right. Let's again put it in perspective of BHA method, just that we are trying to align to that kind of method. So basically in BHA method, you say like the hypothesis is the lower input, right? So the number of, so the input here for us, we have to reduce the input and solve for that. So here for us, the input is, again, if you look at all the 3 problems that we are looking at, the pattern is like you have given an inputs and you have to reduce the inputs and solve for it. If it was 1 disk, how would you solve? 2 disks, 3 disks, how would you solve? If there are like 8 numbers, how would you print? 7 numbers, how would you print? And if you have like a stack size of 1 to 7, how would you do? Like if it is 6, 5, 4 and all, right? So that's the kind of a pattern where you're reducing the input, and that's where this BHA method kinds of helps in solving those problems. So in this case, the input is the number of disks here, and now we can have an hypothesis saying that okay, whatever, if the n is the number of disks that are given here, and we can assume like okay, the hypothesis is for n minus 1 you have a solution. And how would you solve for the other disk, right? So I think in this case, so in this case, so if you took it like for 2 disks, so you say like okay, if I had to move from here to here, I have a solution for this one. And then, and the induction here is like you move this one and then you move this to here, right? So you solve for 2, and then, and the induction is like whatever is left, you move to the destination and move this one here. So that's the method kind of followed here. It's little not straightforward, but again, it followed that approach. So, so again, though the problem looked like you have to do so many things to understand and calculate it, but if you apply this approach, the hypothesis approach, So here we have like 3 disks, which is like source, destination, and helper. We just have it as numbers, and the number of the 3 rods, source, helper, and destination, and the number of disks that's n. So first we come up with hypothesis, which is like we solve for n minus 1, right? And that's the hypothesis that we have. And then so here what we, like I was showing earlier, so instead of instead of using the destination, I'm using the helper as the destination to solve that problem, and then for the n minus 1 rods. So now I assume that I have solution for that hypothesis, and then the rest of the induction is like moving the disk, whatever is left, that is like n minus 1, and we always solve for the n, right, from source to destination. And then again we solve it again for the rest of the ones which are on helper to the destination. It's a bit tricky, but kind of using that hypothesis always. Did it make sense, guys?
So this is something we can relate to the pattern what we are seeing in the graphical way, right? So you are trying to just annotate that in the code. I think that is what is making it little simpler to understand, I believe.
Yeah, but graphical problem is trying to solve it, but what I'm trying to relate more to is like the approach of using hypothesis and induction way to solve this problem. Hypothesis is always like, okay, now you have a solution for n minus 1, and then you only handle the n case, and that kind of n case and the base case that solves the problem. So it's like you're not really solving for each and everything. What you always make an hypothesis that n minus 1, it solves it, and you only deal with the nth disk.
Is it helpful to think about the hypothesis first before the best case, or go to the best case and then the hypothesis?
I think either way is fine, because hypothesis is pretty straightforward, right? You make an assumption that for n minus 1, it solves it, and the base condition is always the lowest possible input, the least possible input, least possible valid input, right? So in any problem that we take, if n is 1, that's the least possible thing, and you say like what you do with it. That's the only one, so you do what you do with it. Even in the reverse case, you say like if it is empty, what you do with it. And hypothesis is always top minus 1, because in the stack we cannot do minus 1. We pulled out the top and we said like, okay, deal with it. And even in the print case, you said like n minus 1. It's either way is fine, right? Induction is the core logic. Hypothesis is like you assume that would work. Base is like you say like what is the least possible input. So that either way is fine.
Okay.
Generally, hypothesis goes first. But in other ways of solving recursion problems, people say like solve for the smallest one and then pick from it. I think that works for other ways of solving the recursion problem. Here it is here because we are using like this method, hypothesis makes more sense.
This is because it decrement by 1, right? So it's easy to see the best case, but in some other problem, maybe did not decrement. So the best case may not be obvious. I think, yeah.
The base case may not be obvious. Okay. So in other cases, like Can
Yeah,
you
I think
think
was
of an example?
like coin chain, right? So
Mhm.
that the always decrement by the amount.
Mhm. Yeah, yeah. So there, that's a different problem, right? We are not trying to decrement the input. It's like there you have like choices of like what you have multiple choices and decisions to make. So there, this BHI method will not apply. I think that's the next approach that I'll talk about when you have choices and decisions that you have to make. Well, like this approach is not like a generic one that will apply for every problem. This applies for specific kind of problems where you actually decrement the input, uh, decrement the input in that incremental way, to reduce the input. So this is one approach. I mean, like the way I started, right? Recursion, like there are multiple ways people think about solving those things. Whatever fits for you. Like if you already have a method to solve this, if you already have a way to solve this recursion problems in some way, you could always go with it. Whatever you are comfortable with. It's just like I've found this something interesting while I was looking at different things. So I believe like I've seen this in some other place also. I've looked at it from one channel I'm looking at right now. I'll share the link. Aditya, he has a pretty good DP also, dynamic programming. So from where I picked this recursion, but I think I've seen in some other university notes also like use the hypothesis way to solve these problems. And I was looking up about it, like this method of solving in discrete mathematics also, there is this method of solving actually hypothesis induction or something. There's already a known mathematical way. So I believe like somebody who's solved those problems, this would make more sense for them. Okay, so yeah, that's to introduce to that kind of an approach. We can
I have one confusion.
Yeah.
So out of these 7 steps, which are those steps which have been performed in the induction part?
Which are the steps that are being performed in the induction part?
Because we are making 2 recursive calls, right?
Right.
One on the line number 9, that is the hypothesis, right?
9 is hypothesis, and this is induction. These two are induction.
So line number 11 is the induction part and printing statement.
Yeah.
So can we like go through which are the steps which are being done in the induction part?
I think everything is in induction.
Okay, so if we say that we have 3 rods, the one you showed in that puzzle, so are we considering the last rod to be the one at the bottom or the top?
Last rod to the, I didn't get it. Last rod to the bottom.
Because,
like
so you pass n-1 in line number 9. So you pass the first 2 rods or the bottom 2 rods?
I passed the first 2 rods.
Passed. Okay.
Yeah. So source destination, source helper destination. So I made helper as the destination.
I'm sorry. I meant the disks. Sorry, the first 2 disks or the last 2 disks. So you're saying the first 2 disks you're passing.
Yeah, first 2 disks. Okay. We say like we solve for the n-1 and then what to do with the rest of the one which is remaining.
In Naga, is it not the line 9 and 11 both hypothesis and the 10 will be the induction?
So for overall, this is hypothesis and this is induction, right? We say like this will be solved for -1 and this, but to even for the rest of the pieces, I believe this is becoming hypothesis. For the 2 that are remaining to move to the destination.
Mm-hmm.
Yeah, that's the reason it is not straightforward as it is. It's a bit tricky, but kind of following that approach. Like you always assume like, okay, whenever you want to solve for n, you say like, okay, n-1 is already solved and you only solve for the rest.
Yeah. Thank you.
So the line number 9, we are saying like we are moving from source to helper using the destination rod. And
So
in
helper using the destination only.
line 11, we are saying that we are moving all the disk from helper to destination using the source.
Using the source.
Gotcha. Go do 200 math problem, đi chứ.
100 math. Okay, Leon, I think you're not talking to us. Okay.
Oh, sorry.
I know where that is coming from. 200 math. Okay. So yeah, if you guys want to try a few more with this, you can try this. Like, I'll share the channel. We talked about a few more of this approach. You find it interesting. You solve it quickly and like clean solutions. So with that, I think we can move to the next problem. This might not take a lot of time, but if you have any questions, we can continue to do that, or we can move to the next method.
Just a small thought. I mean, what would be the complexity? I'm not able to visualize.
It differs from 1 to 1. For the Tower of Hanai, or in general for this kind of?
Tower of Hanai, this implementation only.
Okay, let's take a look. So this one. Move. I think off and square.
Okay.
Yeah. Off and square, I don't know if it can be done in off and method, because that's the only way this problem can be solved actually. I don't think there is like an optimized way to solve it.
Yeah, true. Okay.
Yeah, I think it's not OF. I think it's not OF n square, because when we increase the number of disks, the count what we have as a variable, it's incrementing, I think, exponentially, or like for 7 disks, it became like 127 moves, right?
Right.
So.
Oh yeah, it's a straight correlation.
Yeah.
Yeah.
So I think the count is, because we have a count variable, right? So there is a relation between number of disks to the number of steps it went into the recursion. So I don't think so it's n square for sure. It's
it's not n square, because we clearly have moves and the number of disks. The input is 7 and the moves are 127. So I believe here it's not more about complexity.
Is it like 2 to the power of 7, or I don't know?
Somebody is writing here.
There is the recurrence relation which I mentioned.
This is the recurrence relation. Mm-hmm. Can you?
Yeah, for the Tower of Hanai. So if you solve it, it will be somewhat order of 2 raised to power.
Yeah, it's 2 power n, I think.
Yeah, and the number of disks will be 2 raised to power n minus. Like if you use back substitution and solve this recurrence relation.
Oh.
I can share the link with you.
2 to the power of n minus 1. 64.
So Naga, can we make it like this to be 16 and then see what is the number? Is it like 2 to the power of 16?
Yeah,
I think
it
looks like it is to the power of 6. Yeah, I think it's going in that.
n minus 1, but I believe we should solve it using the recurrence relation. Right? 256, 255, so 32, 31, so. Okay. I don't know if the complexity is the goal of doing it. The lowest complexity is the goal of this problem, because I believe there's only one way to solve that they have found to solve this Tower of Hanai. It's more about getting the steps, is what I believe. Not even the count, because count is a mathematical solution, right? 2 to the power of n minus 1. So. Okay.
This will turn into some. T of n will be equal to 2 raised to the power t of n minus 1, and keep on decreasing. Then it will be 2 raised to the power n minus 2. and so on till 1. So if you solve this, this will go till 1. I mean 2 raised to the power 0 till that point it will go. And if you solve it, it will be like order of 2p power n minus this 1. So which is overall like 2 raised to the power n.
Yeah, it looks like a GP.
Yeah.
Looks like GP. I mean,
The geometric progression.
okay.
Yeah, you can proceed. Next question. Yep.
Thank you. So the next one is also I think it's a very common problem, but the next one is again a problem where we want to use a different approach, which is recursion tree method to solve this problem. So so in this method, what we have is like a, every time you want to go forward, you have a choice and you have to make some decisions to move into the loop. We already know this is a recursion problem. So every time you have to make some choice, you have to take a choice and make some decisions to do this kind of problems. And we can talk about the approach of how we can build this recursion tree and how we can convert that into code. So I know this is again a very common problem. I'll just give a couple of minutes to go over for you guys. For anybody new, I think it's generating the balance parenthesis. So for example, like if you are given n is equal to 1, the output is like 1 open close. And if you have given 2, that's like whenever the input is 2, that means like you are given like 2 open, 2 close. And with that, how many valid parentheses that you can make. So here, this is open close is one different, and open close is one. Like we have like two sets here. So given a number of parentheses, how many of those you can make is the question. So again, like this is one more approach, like BHA, right? This is one more approach of solving this kind of problems. How we can build that the recurrence tree and then derive code out of it.
You can use backtracking also.
Sorry?
You can use backtrack for this problem, like.
Here, in this approach, we are not using backtracking actually. I mean, like at least the solution I'm going to talk about, because building the recursion tree with the building recursion tree. But yeah, that I believe that's also one approach.
A similar problem was there on lead code, like generating all the balanced parentheses.
Yeah, I think this is a very common problem. I felt this is not a.
You generate parentheses, exactly. Somebody has shared it on the chat.
Yeah. I think this is not a. At least from what I have seen with the approach that building a recursion tree. When you talk about recursion tree, it's not the stack tree that I'm talking about. I'm talking about in a way of building the recursion tree using input-output method. Like, what is the input given? What is the output you generate? And how do you get to the base condition? So that's, I'll talk about the approach, but if there is anybody have any solutions using recursion, please feel free to share it. And like, if you want to share your code or talk about it, that's fine too.
Yeah, I think we discussed this problem sometime back, and we just take two variables like a open or a closed, and which is just either you initialize with 0 or you initialize with n, and you keep on adding opening bracket first, and in the if condition, and as soon as you hit your n, you in the other next if condition you start adding a close bracket, and that's how the process goes.
Oh, okay. So they
Yeah, again,
there you would use backtracking, right, Sumit? Because you keep adding the open.
Yeah, I think you can say it's internally it's using a backtrack because we added all three. So I think like if we take an example of output 2, right? Maybe the output for n equal to 2, the second output will come first because we end up giving all the opening bracket first and then start giving closing bracket, something like that, I guess.
Yeah,
Yeah,
I
I
mean,
think
the way I always think about backtracking is like you make an operation, and then afterwards, if you actually undo that, I take that as a backtracking. So
Yes.
the approach that you're talking about, we do that, right? We keep all the open, and then we undo the open after we perform an operation.
so. Here we
Yes.
don't
Yes.
actually need to do backtracking because we just need to return a count.
No, we actually
Oh,
print.
we need to give the. Okay,
Yeah,
we need to print it. Okay,
yeah, all
so
of
I
it.
think.
generate the structure
Gen-
also, right?
Yeah.
Mhm. So I think, like Sumit said, there are two ways. Either you backtrack or you simply keep on passing your new input to the next level.
Right.
There you can just use a string, and then internally you are not doing backtracking, but you are generating a new sequence that's like in the memory. So here, if we introduce the backtracking element, then you have a constant like a string builder, which you're using to, like Sumit told, like the second example, first you put all starting, then put all close, then coming back, you remove the second starting, and instead of that, you put a close bracket.
Yes. Yes. Yeah.
But if you are not using a fixed memory like a string builder, you can still use a string and keep on putting your new answer to the next level, and no need to come back and clean it.
Yeah, I don't need to come back and.
Yeah, that can be passed as a parameter, like whatever is our output string is at that level, that goes as an input to the next recursive call.
Mhm. And then we had this start and opening and closing to keep track because your close should always come after opening.
Yes, yes. Yeah, I think there is one trick to handle that case. So I think we could, if you want, we could do the backtracking if somebody wants to share. But
Can
the,
we, this is the recursion, right? Can we go with the recursion first?
yeah, that's what I was proposing. Like I'll go with the recursion approach, and also specifically about the approach that they talked about here, like the building the recursion tree. So I'll share one. The tree that I have built, recursion tree that I have built. It's difficult to do it here, drawing here. So I've had it on a paper and then I took a picture of it. I'll share that. Okay, can you guys see this? Is that clear?
Yes.
Okay. So, so to build the recursion tree, what he talked about here is like, you use this, one is that BHA method that I talked about, and the other is like building the recursion tree to get to the solution. You use the recursion tree kind of a method to solve problems where you have like, you have choices and decisions to make. Here, the choices you're given here are like the open close uh, uh, open close braces, and then you have to make a decision on which one to choose, right? So in that kind of problems, you building the recursion tree kind of helps. I think this. Okay, building the recursion tree helps, and in this we call this also like input output tree, where you define an input output that you want to do and keep reducing the inputs. that's the method to follow to build a recursion tree. You take the input output that you want to do and keep reducing the inputs and build the outputs. So that's how you build the recursion tree. This is not like a stack tree. Like I know, like for solving the recursion problems, like in several places that you actually have a stack tree where you keep track of the stacks and all. Here we are just building using the input output. So, so here the input that is given to us is like the brackets. Here it is given like 3. For example, we take 3 as an input, and so 3 as an input. So you have 3 input brackets, 3 output brackets. And to start with the output of this function, each one is a function call here. So each node, for example, so okay, let's just focus on the tree for now before getting into the function. So here you are given like 3 open braces, 3 closed braces, and then you are trying to build an output, and you are ready with an output when you have used up all the open and closed braces. And now you have choices to pick and decisions to make. So the number of options that you have becomes the number of nodes, number of child nodes you have for this decision tree. So here you have, every time you start with, you have like 2 options, whether to choose an open brace or a closed brace. So here we could choose either of them, but we know that having a closed brace at the start is an invalid one. So we don't do that. But in this case, it's invalid, but there are some other recursion tree cases where you have like clear choices. You could put either of them and both of them will become valid. So if you're like trying to build a combinations of a string, you could pick any of the character and that still becomes valid. So here we have that condition. So you build this input output nodes. So every node is an input output node. You build this input output nodes, and the number of nodes is number of choices that you have. Number of child nodes is number of choices that you have. Here you have one more choice, but that's not valid, so you're not building it. So you have output, input. So in the output, you choose like open brace, and then you reduce the input. So the left one is output, this is input. So that's how you build this recursion tree. So
Naga, so whenever you had an invalid choice, you used to backtrack only from that area, right? Like
yes. Here we are not backtracking it. We are not using the backtracking approach. So here we are like avoiding to use that invalid approach.
Okay.
Avoiding to build the child node, make the call like the child call. In this case, child node is like child recursion call. So we'll avoid that. And we know how to avoid that. There's like simple way we could avoid that. One is like, we can look into that. So in this case, it's pretty straightforward, right? So we cannot have the start as a close. So we choose only open and we decrement the input. And again, like you have this as output already. Now you keep building the output using the input and you keep reducing the inputs. So for reducing the inputs, you use the choices that you have. Choose left or open or close. So you have open here and you reduce the input and you have like 2, 3 now. Now you have 2 choices to pick open or to pick close. So if you pick open, you have output as like this and input get reduced. And again, now you have, since you have open, so you can use open or close. So so I haven't put like open or close, but whenever the open decrements, that's the open. Whenever the close decrements, that's the close. So you're building the output by choosing the choices and decrementing the input. You're reducing the input. Reducing the input is the core, and using that you build the output. So once you have reduced the input to completely zeros, then you have what you need. But here the special conditions that we have seen are whenever I think whenever the the close. So I think whenever we have open and close are same, then you can only pick one option, that is left. Right. So if you see all of this tree, that's the logic that you used instead of doing the backtracking way, because it's very clear that you know that whenever you have it like that, that becomes an invalid close bracket. But the idea here is to build a recursion tree. You use the output that you want to build and the input that are given, and keep reducing the output, keep reducing the input using the choices. The choices here for us are clearly open and close space. Either you pick open or close. If you have more choices, then you have like more nodes and more trees. Did it make sense, guys?
So you you always prefer the open first, or it doesn't matter?
Doesn't matter. We have to handle it. That's a decision you make. So in this case, you say like whenever you have both of these as same, the open and close as same, you cannot choose close. So you only choose open and call the function, recursion function. So that kind of works because you have that decision to make.
Otherwise, it will become an invalid state.
Yeah. Instead of using that backtracking, it is a straight recursion, right? So to call, before you call the recursion, you actually make that call like, oh, what is the input that is given to me? Is it valid or not?
So I think the other approach which Sumit and I am and Shashank was telling was also similar. It's not different from this. But I think when you will show code that time, we can point out that where we were thinking the backtracking thing could be backtracking word is overused here. It's just recursion.
That's the reason I was thinking like, I think about backtracking whenever like you specifically undo a step that you have done in the earlier step. I think that's only in those cases I take that as backtracking.
Okay, probably once you
do
show your
that.
code, then I can show mine, and then it's a good discussion.
I think it can be used interchangeably, but since it's driven by n as an the number, maybe the backtracking I've seen like it comes into mind when we have some extra buffer we are adding to a list and then remove from the list. Those kind of thing, right? Like the n queens problem or the Sudoku problem, where you have taken certain steps and then you go through a recursion, and when you come out of it and you know that it's not a valid step, and then you remove that step from the right. I think maybe it can be used interchangeably, but yeah, I don't know. But one question I had, Naga, is that we can see the code, but are you taking two separate variables for as it is shown in the diagram here, or is it like you do it with one variable?
No, I'm using separately because I need it separately here to build this output, right?
Okay, I think
I really need to know like what is the output and input. So that's the reason like here basically this approach is talking about having the clear inputs, and whatever input that you want to reduce here, that has to be like specifically mentioned. So here we need to have like, what is the number of open inputs that we need? What is the number of close inputs that we have? And we consider the output as a valid only when all of this is reduced to 0. So reducing the inputs is the way to build this recursion tree.
Okay, so we are not going in depth on like, if I see the left side of the tree, we are not going in depth on one side and closing on one combination, but it will suppose at the level 1, 3, right, where we have 2 opening brackets. So it will split into 2 different calls at that point. Maybe we'll see the code and then we'll have more understanding, I guess.
Yeah.
See, I see in this, like, if you compare, you count the number, of character at each level of that tree right there. Can you go back to that tree, Naga?
Oh, sorry.
Yeah, so the number, let's think of in terms of the level 1, 2, 3, right? So we see that, at each level, the number of characters always the same, right? So I think that's how, we can make it like backtracking. Because if we go level by level.
So when would we do the backtracking, right? Here, before we even go into the loop, we make a call whether we need it or not. We know whether it is valid or not, right? So we never have to go back to backtrack. In this
But if we think in terms of backtracking, because at each level we have the same number of character for in each string, we can make it even, the last character either open or close.
I didn't get that, but last character is either open or close.
So let's say
I'm trying to make sense of like, I'm trying more to see like, is there really a backtrack or a backtrack need here? So you're saying like we are, or like we, it could be done in backtracking. I didn't get that part actually.
I think, okay, go with recursion first and then.
No, I'm sure like it can, I think it can be done in backtracking, but I think in this approach, we didn't do it and there's no need to do it.
Yeah.
Yeah. Okay. So let me stop here. Okay, so so that getting the tree that we have built, that getting converted into this function, right? So we know like we want to build the output, so we have what? Sorry, yeah. So output is this is the function. Like I said, each node was a function. So output is the output string that we are building, and we have like open and close braces count. This is just to build it all into a vector of strings, but that's what it is. So we have the base condition where when we reach the end of the function, if open and close are 0, then we just push what we have so far in the output string into the answers. So when we started, we said like if open, so open is not equal to 0. Oh, sorry, I kind of forgot this one. Open is not equal to 0.
I think that's correct, Naga. When it is not 0, then only you want to go inside.
It's not 0, we don't go inside.
Yeah, if you start with 3, then it will 3, 2, 1. Once it becomes 0, you will do the top if statement. And
yeah.
And then if close is 0, you are done. You do return. If it is not equal to 0, you go inside. Once it becomes 0, you go inside that other if loop where close is greater than open.
Yeah. That's right. So whatever the, so what we did is like whatever the output we have so far, we are appending open into it and then decrementing the open and calling the function. And then again, this is the condition I think we always want to make sure when we get an input, the close is greater than open. If not, we don't want to go into that condition because that becomes an invalid case. This is where we said, like, instead of backtracking, we are checking this condition to make sure we don't go into that invalid condition.
So, Naga, so where I think we were trying to say backtracking was at line 54. Instead of using a string, if you use a string builder, then so I don't know how string works in C++. When you do a pushback, it creates a new string there.
It doesn't create a
No,
new string.
it's the same string, yeah.
The same string.
So is it pass by value or pass by reference?
No, you already did at line 53. Okay, so when you do output is equal to OP1, it creates a new string there at line 53.
Yeah, we are using, yep, you're right. Actually, we are creating a new string implicitly. Yep.
So same concept of immutable for strings, right? In C++.
No, in C++, actually, when you append, it doesn't actually create like a new string and do it.
Okay.
As far as I remember.
The strings are mutable in C++, yeah.
So then if you make any change, it should create a new object. Otherwise, it won't work if it is not creating a new object. Because otherwise you have to remove it. That's what my understanding is.
Yeah, I think it depends, as Asim said, right? Is it pass by value or pass by reference?
Is it pass by value here?
Which one?
It's passing by value.
The string is passed by value.
Right, yeah.
Okay.
Value.
Okay, yeah. So I think then it should be fine actually, because every time it will
create
add
a new copy.
Yeah, new copy basically, and then pass it for that particular stack call. That will be the concatenated string will be the new input as a OP1 or OP2.
No.
I think yeah.
So I think
if you
line
pass
50,
by reference, then you'll have to do a backtracking. Yeah.
Yeah, if you pass by reference,
Because
you have
exactly, I think Santosh mentioned that, like, if it is passed by reference, then it will keep on concatenating on the same string. Then we have to do a backtracking, right?
Yes,
right.
backtracking, or in terms of we have to clean it. Like you guys mentioned earlier, like in N queen problem, we go one full path, and if we can't get the answer, we come back. But here we are actually getting answer.
Yeah.
So don't know if we can call it like a full-fledged backtracking, but yes, we are adding thing and removing thing, and if that is we want to term as backtracking, then yeah, it's fine.
Yeah, I think it's in sense it is backtracking. Yeah, yeah.
But in this case, we always get the correct answer, right? So it's not a backtracking, because we always move to the valid direction.
So if it is an invalid, we don't even go into that direction.
Yeah.
So we check this to make sure, because for us, if the check is not like finding the destination path or something. So here we know exactly when we are going in the direction, whether that's valid or invalid.
Yeah, I think I believe it's not backtracking, because we are not adding invalid input to the output. That's what I feel. I'm not sure, but
Yeah, that's what I understand. That's the reason I was telling, like, unless I do an operation and undo that operation, I would never consider that as, in general, I wouldn't take it as backtrack. And again, here, we don't take a wrong step to backtrack here. So even if we pass string as a reference, where would we pass string as? reference, because we need it for, we need like several different combinations of that output, right? It's not like one output is what we need.
Yeah, we can't pass by reference here.
Yeah, we need all combinations of combinations of
Is there a case that the condition on line 51 and 57 are not met, and they just run through that and return?
I think that's when both of them are 0. I think that's when the base condition would.
But if both of them are 0, then they're gonna go into condition 46, right?
Yeah, base condition. Yeah, that's the only condition that. So let's say, and that if that's the case, that's an invalid case. If both of these conditions are not met, that's an invalid case.
So do we ever have invalid case?
Yeah, invalid case is where, so for example, if you take.
No, I mean in our code, the way we write, do we ever have invalid case?
Yeah, we could have an invalid case, right? When what we want is we have an, if suppose we have used up one open close, we don't want to have a close before when we already met the open close combinations, right? So if you have an open close and we don't want to have a close there without having a open, that's the invalid case. So I think in the diagram we have a couple of invalid cases that we didn't go in.
Yeah, I think like what Leon is saying is that before even getting to open or close being -1, we will get into the base condition and the code will return from there. So it will never happen that the open becomes less than 0 or close becomes less than 0. I'm not sure if I.
So in this case, right here, so we have 2, 2, and so if you go to the right direction, so the condition what we had was like close is greater than open. So the invalid condition is close is less than open, right? So if you go to the right condition, so close becomes less than open, right? Where we include an open here instead of, we had two choices here in this bucket. When we came here, we had two choices here, either to choose open or close, right? If we choose close, what will happen is we have open as 2 and close becomes 1. And that's the condition we checked in the code to make sure we don't go in that direction. Because if we choose that case, we have open, close, and we have a close there. So when we have that node here, let me write that down here. So here, like we didn't go to the right direction because that's an invalid case, because that would have become like open, close, and become a, sorry, that would have become like this, which is an invalid case. We identified that invalid case by using this one. It would have been from here, because we used up a close, this would have been 2 and this would have been 1. And if you look at the code, we have it like we should never have close less than open.
It should be less than or equal to open, right?
Equal to
For the invalid condition. Because if
that's
it is
invalid
true to
condition. Yeah, less than or equal to, but we only did a valid condition.
yeah, so we are checking greater than open, so that's why we are not going into the invalid condition.
Yeah, invalid. This is the condition where we don't want to get. We never want to have like this, and we are making sure of this by checking this. Always making sure close is greater than open.
Yeah, that is one, and the other one is at the beginning of the
Even this is taken care by that condition.
right, because
So even here, if you had gone to the right, it would have become like, oops, it would have been 3 and 2, right? So that's an invalid case. So we don't go that case. So whenever close is, we always make sure like close is greater than open. So without that, we wouldn't go into that condition.
But
That end up taking care of.
Yeah, that's good. But this coming up with this condition is not very intuitive, right? It's very tricky.
Yeah.
Yeah.
Yeah, that's not very.
That's the key. Yeah.
That's the key actually.
Yeah.
And that's how we avoid the backtracking. Otherwise, we would go check, and I don't know. Even in the backtracking case, we should know like when is that when is it not balanced, right? Some way we'll have to check that thing, like whether this is balanced or not, and that check can only be done with this part, I believe. What would be the other way to do the check if it is balanced or not?
Yeah, if it's a balance or not, just keep on looking for the whole string using a stack, something like that.
Yeah.
Yeah, maybe, but that will add more time. Yeah.
I think that's the logic to check whether it is balanced or not.
Yeah.
That has to be included.
Yeah, this looks very efficient, but the only downside is coming up is slightly tricky. Yeah.
One thing
more than the trick. Sorry.
Yeah, go ahead.
Yeah, I believe more than the trick, what he wanted to explain with this approach is using the input-output method, input-output as the nodes, and reducing the inputs to create the outputs. And to reduce the inputs, the number of nodes to build the recursion tree, the number of child nodes you have is the options that you have. If there are like multiple options you have multiple nodes, multiple child nodes here. So build such kind of a recursion tree, and this becomes a function, and this becomes the conditions. If conditions, and reduce the input and go into the call the function again. Reduce the input, call the function again. Right? If you look at the code again, what we did is like we had a function with input output, and then when we call the function back again, we populate the output, reduce the input. And to call the function, you make choices. You make decisions to call that function, right? So you said like I picked an open, put it in output, reduce the input, call the function, and you have one more choice to make. You do it, you call it again. So that's how you build the output by reducing the inputs. Is what he wanted to explain here. The channel that I'm following. And once you build this recursion tree, then converting it into code is straightforward. Is what we want to do. This condition is like this condition of making sure this is valid is like, I believe whatever you do, you'll have to have that condition, right? Checking the balanced or not is whether you use any kind of approach, you will have to come up with that logic. Either you use a stack or this thing, That's part of the problem. Building the tree is the problem of the recursion.
Yeah, makes sense now. Yeah.
Okay. Yeah, I think Leon or somebody was.
Yeah, I was saying. So I think we can prevent that second string we are initializing on line number 59.
You can prevent the second string that we're creating on the line
Yeah.
number 9.
I don't think we need a separate string for this recursive call. We can reuse the first string we are using, that OP1, because for what we are doing is that we are going towards the left first till our open brackets exhaust, and then we kind of check the other thing. So we can use that.
Oh yeah. Actually, it's like we could use OP1 because OP1 scope is lost once you send it, right? We are passing as value here.
Yeah.
Yeah, that's one optimization.
No, but they are in different scopes, so you'll have to get it outside.
I'll have to.
Yeah.
I think that's a decent optimization, I would say. Yeah. Okay. There are some more problems that if you guys like this kind of recursion tree approach, and if it helps in understanding any other problem better, there are some more problems he mentioned. I'll share it in the Slack channel. Those are again the same problems, combinations. He tried to solve the combinations with this building the recursion tree. I think there's some more like that. So
Where do you post it?
I'll post it in Discord. Actually, I'll do it on Discord. I think it's.
Yes, please do that. Yeah.
I mean, there are some recursion problems where it takes a lot of time to understand, right? So the way picking one of these approaches, if it helps in solving those problems, it's good. It's a good effect. Yeah.
Yeah, I agree.
Could you, Naga, could you outline the step for tree recursion in this function? So we check the basic base case, and then you say we check the input and output.
So I didn't get that line. So what we are saying is we take the inputs and we know the output that we want to build by reducing the inputs. So that's how you build this function. This is the core of it. Always like this is an input output method of building the recursion tree. So you take the output, and this is the output that you want to build. This is the input you have. Base condition is always there, so that you'll anyway have to build. So now when you call the recursion again, you keep reducing the inputs based on the conditions, right? So here, this is the condition. We want to make sure of this one. These are the conditions. But you keep reducing the inputs. And you have two choices. So you have two child nodes, and you have two choices here. And so you call 2 times. If it was like three options that you can make, you will call it like 3 times. So you're just reducing the inputs to build the output until you get to the base condition.
Okay. So you report, because we have 2 input, right? You return one input in one if statement and another input in the other if statement, right?
You reduce one input in one statement.
Become both 0.
Yeah. You reduce one input in one if statement and the other input in the other if statement. And if you have multiple of those kind of options, each one is talking about the number of options that you can take to build the output. Yeah. I think you could also, like, it's a video. You could also go through that videos. You might have more better explanation on this. It's not in English, so yeah, I don't think there is subtitles also. So let's see. Okay, I think that's all I have, unless you guys have any other questions. I'll share those channel and details there. Okay, guys. So, I mean, my attempt was only to introduce those approaches to solving the recursion problems. So, if you guys don't have any other questions, probably we can stop recording, Bhavish.